Yep, we left off talking about acids. So, conjugate acid-base pairs. So we're talking about Bronsted acids and bases, which has to do with proton donation and exception. So, you remember we like to make that distinction because, of course, then we also have Lewis acids and bases, which have to do with electron donation and exception. Now, something we didn't exactly do, we didn't get to this in Gen Chem because it's a more difficult topic, is activity. Now, in a solution, you have to think about, well, how much of this compound is actually active? Like you put a salt. We kind of did this. Do you remember colligative properties? And you have an electrolyte solution.
Yeah.
Well, your Van Hoff factor is never actually ideal. Like your sodium chloride never fully breaks into a Van Hoff factor of 2. Well, it's about 1.9. So this is kind of referencing back to activity, where you'd say, well, these solute particles are interacting, and so how much of this solute is actually involved in solution processes? So that's really going to be your idea of activity, and it's going to reference back to what we call chemical potential. And so that's your energy absorbed or released when the number of particles of a species changes in a system. So it's like if I start putting more, I would say a good way to think about it is you put water into a concentrated acid versus a dilute acid. What happens in the concentrated acid?
It'll like rip the water apart, right? Like
yeah, but how do you know energy is released?
Like it'll release heat, right?
Yeah. So that's kind of this whole idea.
Oh, okay.
Now, your chemical potential, the easiest version of it, so it's going to be Greek letter mu, and then G is going to be your Gibbs energies. So you'll see those either called Gibbs energies or free energies, or.
And that's the like G equals what is it? H minus TS? Is that what we're going to use for it?
Yeah. Not quite for this one, but no, this one, that is one of the versions of Gibbs energies. We have another version that we'll work with for this in particular, but you will see the H minus TS show up when we talk in the next section when we're talking about, like, for example, the strength of hydrohalic acids. That's an interesting question. Why do I call what is a hydrohalic acid?
It's like the HCl.
Yeah, and why is it hydrohalic?
Hydrogen in the halide.
Yeah, there you go.
Yeah.
So I mean, when you break it down, it's actually pretty simple. But you'd be surprised how many people hear these words. I don't know if you call it halic or halic. I don't.
It's a compound word.
Yeah.
Complicated.
But most people hear these words and they go, nope, I can't. No, it's just a hydrogen halide acid. But we'll get to that when we talk about the Hess cycle, which we talked about Hess's law on Gen Chem, but we didn't do the Hess cycle because you don't want freshmen going, nope, I can't do this. Nope. It's not that the Hess cycle is hard, but you need to have some chemistry under your belt to see what it's doing. But we're going to be talking about chemical potential here. So it gives energy over either number of particles or moles, because the two are going to be analogous to one another based off the systems we're talking about.
Sure.
Okay, so let's start out with our basic differential equation with one of our basic differential equations for Gibbs energies. So our state functions. Have I ever talked to you about state functions?
Yeah, I think I've heard the word before.
Do you know why it's called a state function?
I say no.
So state functions are going to relate properties so just like it sounds like, relate properties in a given state. The key to a state function is they only care what your beginning state is and your ending state is. They don't care about pathway. There are other thermodynamic properties that are dependent upon pathway. State functions are not.
Sure. Okay.
So it's like, where do you begin? Where do you end? I don't care how you get there. Do you go along the diabet? Do you go along the adiabet? They don't care.
Sure.
Okay, so what we're going to do is we're looking at a system where we don't want it to be too difficult, like a system we can't solve. So we're saying, well, this is going to be a constant temperature system. And do you remember what the differential of a constant is?
It's just 0.
0. So if t is constant, that term goes to 0. So we're going to get this differential equation. And then we remember that V in RT over P. And what we're trying to do is get to a more common expression of chemical potential. Okay, so this is going to mean that we now have and this is what I always tell people. Yeah, we use calculus in physics, but a lot of what we're doing is algebraic manipulation until we get to something we can solve easy. Because it's like I can solve differential equations, but nowhere near as good as Gregory.
Sure, yeah.
So it's just
You just make it easier.
yeah. So physicists, we kind of cheat a little bit. We do so many things that make mathematicians angry. Like derivatives are not a fraction. And I can treat them like one. But so now we look at our initial equation. We see that our Gibbs energy is N times the chemical potential, which means if we have a Gibbs differential, if you're going to differentiate the other side, one of those is constant, one of them differentiates. Which one do you think is going to differentiate with Gibbs?
Probably the chemical potential.
Right. The number of particles is going to stay the same, and that's a constant. Okay, so there's our differential. Now I'm going to start using primes because we're going to integrate. And again, this is something else that drives mathematicians nuts. I can't integrate mu with limits of mu. I have to have like some kind of stand-in, like mu prime or whatnot. Sure. So trying to do some things to make sure I don't get hate mail from mathematicians.
Yeah.
But
a math professor is going to walk by and is going to get angry.
Oh yeah, they'll walk by and go, "What the? No. And we're going to start using P prime as well, because this side is going to have limits of P. All right, so the ends cancel out, and we're going to integrate. Okay, right there. Yep. Of course, in physics, your sub-zero is some initial value. I need to relook this up. For the chemical potential, it's not just an initial value. I think it's like a pure compound, something like that.
Like some sort of standard.
That, or it's like the chemical potential of the ideal. I need to look it up again to remember what it is.
So that would be dependent on what you're working with?
Yeah.
Yeah.
Let's see. R and T are constants, so we know those can come out of an integral. And so this is why I always tell people, if you take statistical thermodynamics, learn your exponentials and your logarithms, because that's pretty much what you're going to use over and over and over again.
Yeah, I see that natural logarithm there.
You see the definition, the 1 over P prime dP prime, you see that's my definition of the natural log. Okay, so, and of course we know integral of a differential just gives me back integral dx just gives me x, you know, so this is going to be just don't want to run myself out of room. Yeah, probably need to do this. Okay, so it's going to give me mu prime. I'm going to evaluate this. Mu zero mu. It's going to give me RT natural log P prime P0 to P. So that means I'm going to get mu minus mu zero equals RT ln of P minus natural log P mu zero. And so inevitably what we get is we're going to get our chemical potential. It's going to be mu zero plus RT ln of P over P0. Now, we're getting to the point where we can use this for solutions. You see that this is, of course, this would be, of course, usable for a gas. But we want to get to the point where we can use this in terms of our activity. Now, when we talk about gases, we can talk of an effective pressure called a fugacity.
Fugacity.
So it's like you can say I have this pressure, but how much of that gas is really contributing to the system? Mm-hmm. And so we call that the fugacity. And so we're going to say that the fugacity of gas I is going to be a fugacity constant multiplied by our pressure. So you can see that the fugacity constant is actually going to fractionalize that pressure and give us an idea of how much is actually contributing. All right, well, we can now put these in. So pressure all right, so that means chemical potential. Now RT mu zero plus RT ln. Then we're going to have fugacity phi down here. Let's be writing that as superscript. I was. That makes more sense. Let's change this to that. Oh. Now it makes more sense chemically.
Yeah.
Standard states.
Okay, I'm getting it. I'm understanding.
That's what it is. I just put the zero in the wrong place. I was like, my brain kind of went, see, that's why I don't stay up till 3 in the morning prepping. But so now you see that that's actually a standard state, which means that your integration limit has to be the standard state. And we'll just correct this one and get the idea. There we go. All right, now that's the fugacity in the standard state. Now here's a question. Why did I do fugacity as standard and non-standard, but left phi the same?
The phi.
But your fugacity constant. It's a fractionalization constant or a proportionality constant. Right. That's going to give you an idea of how much that gas is participating.
So because it's a constant?
Yeah, yeah, and so more than that, because it doesn't matter if we're in standard state or some other state, it's still the same gas. So the fugacity constant for that gas is going to be what it is. Okay, so then those are going to cancel out. Okay, now here's something that that I'm just going to give you this equation because it's another derivation that we can do we can do someday, maybe physical chemistry or something. But fugacity itself is going to be gamma so our standard state fugacity multiplied by gamma and chi. Now chi you should know.
Yeah. Yeah, I should. Oh my gosh. From what?
In chemistry, what is chi?
I don't really remember. But
Mole fraction.
Oh yeah.
So it's the mole fraction of this compound. Gamma is your activity coefficient. And so your activity coefficient multiplied by mole fraction multiplied by the standard state fugacity is going to give you the fugacity of the actual system we're in. Okay, so and now the standard state fugacity is going to cancel out. Okay. Now we have our activity coefficient gamma multiplied by mole fraction. So again, mole fraction, you think about that, you're worried about a specific compound I.
Mm-hmm.
And so you first off, you have to know, well, how much of this solution does compound I make up? Great, mole fraction. Then how much of it is actually going to be contributing to the chemical system? Well, you need another proportionality constant. There's your activity coefficient.
Mm-hmm.
So you're getting you're getting a fractionalization of a portion of the solution. And that tells you how much of this one compound is actually participating in the solution.
Right.
And so, of course, that means the activity of compound I is going to be the activity coefficient gamma times chi, it's times mole fraction, and we end up with a more common expression. Now we have a chemical potential we can use for solutions as well.
For sure.
So there's other ways that we can look at. So one of the ways we get this activity is we have to think about if our mole fraction, moles of compound I, this is another way to express mole fraction. And then what we're going to do is we're going to we're just going to bring in the same thing for both top and bottom. So again, that's essentially like multiplying by 1. What is moles over kilogram?
Moles per kilogram?
Mm-hmm.
It's like the opposite of your molar mass, huh?
Yeah, what's that other one?
What's that? Molality?
Molality.
Okay.
So then we'll have the molality compound I over the molality of compound I in the standard state. So
Oh my gosh, molality came back.
mm-hmm. And so this now means that here's our coefficient. So of course, again, kind of help us remember. And then, of course, your standard state molality is going to be 1 for particles, solid an ideal solution, which means that our a more experimental way to think of activity is going to be your mole fraction times your molality, or not your mole fraction, your activity coefficient times the molality of the solution. So this is something. So this is a different formulation that you could take into a lab and actually measure. So we always like to kind of give equations that can be verified experimentally. And so you can just take that and do that. So we'll come back to use this at some point, but I wanted you to see chemical potential and have an idea of how these compounds are actually interacting. So you know that in a real solution, you're not getting this ideal situation. So we have to start understanding everything through the idea of chemical potential, activity, so on and so forth. And so again, chemical potentials are usually going to be pretty, you can usually look those up for various compounds. So one thing you can calculate is, of course, the activity of your compound in solution. Let's see, is this? We can add, so again, some of the things we work on when we talk about concentration, we have a couple of rules here. We can say, well, activity can be approximated to just your concentration in this circumstance here, and that's how we'll start to understand things. But just knowing in a real situation, you're not actually meeting these two criteria, so you're going to have to go back to actual activity and chemical potential.
Yeah.
Okay, so we're going to start talking about some different types of acids. Now, the book put these in, so I wanted to cover them. These could be inorganic. You see these more in organic chemistry or carboxylic acids.
Oh, yeah.
And why, for example, are these called carboxylic acids?
I really don't know. I mean, the oxygen and then the carbon.
What's that called?
I mean, is it just called a carboxyl?
Yeah, it's your carboxyl functional group.
Oh, and it just has the H on the end, so it's mass. Okay.
Sometimes you see it written like that. It's your carboxyl group. Now, one of the things we're going to really want to pay attention to is a lot of these acids are going to have hydrogens bonded to oxygens. That's going to kind of be key for a number of these. Now, there are acids where inorganic acids, where let's say you have a phosphorus group bonded to this carboxyl group, well, then that's going to destabilize the resonance in the molecule enough that then this carboxylic proton is no longer acidic. So it does shift as time goes on. So sadly, with structures of acids, there is some memorization that just kind of goes into it. Because you would, some of them you're going to have to look at and go, well, yeah, but that carboxyl group is bonded to this large inorganic atom that has this kind of valence structure. So that's going to destabilize. So if I remove that hydrogen, I'm not going to get enough resonance to restabilize the compound. So that's no longer a acidic proton.
I see. Okay.
Now, down at the bottom right, do you recognize that acid?
Sodium hydroxide. Wait, bottom right?
Mm-hmm.
I mean, methane and then carboxylic acid.
So you have a carboxylic acid.
I mean, I guess I don't know what its name is.
That is your acetic acid molecule.
It's acetic acid. Okay.
Mm-hmm. And the book does this fun little thing with notation that I want to cover to make sure you understand, because another way you can write this, so there's a chemical formula, can be written this way. Sounds like a Pokemon, a Miku.
I like that.
But this kind of notation, it's shorthand. Again, we want to get used to shorthand notation. What do you think this means?
Methyl.
Methyl. It's a methyl carboxylic acid.
Yeah.
So you see the carboxyl group and then the methyl group attached to it.
Yeah, I've seen them do that with like methanol, like MEOH or whatever.
So just as long as you're getting down these shorthands and what they mean. So when, again, you're in a lab, you're reading a procedural book, you're reading articles, you're not going, what the heck does that mean? Because that's going to be kind of important.
What element is that?
But now this is a new way to talk about acids. When you were in general chemistry, we talked about monoprotic, diprotic acid stuff. Now, I would say a more proper way to think about these is, for example, acetic acid is called a monobasic acid. But it's not a base.
Sure.
So what does that mean? It's called monobasic because its proton reacts with one equivalent of a base.
Sure. It only has one proton to donate. Is that what it means?
Well, technically, yeah. But let's think of it more in terms of the equivalent of a base.
Okay, sure.
So when we talked about, you remember talking about normality?
Yeah.
Okay, so normality deals with equivalence. And so if you look at, so what is a base put into water that's going to dictate its equivalence?
That will dictate its equivalent.
What does it put into solution?
The strong bases, the ones that put OHs in?
They put hydroxides. All bases put hydroxides in. That's going to dictate its equivalence. So you just kind of take a look at the base and analyze it, and you can get an idea of how many equivalents it's going to have, and then say, well, how many of those can this acid neutralize?
I see. Okay.
So that's what this is mean. This means by monobasic. Now here you see the carbon-carbon structure. So this carboxylic proton is acidic because, of course, now if that proton breaks off, so of course. Okay, so if that proton broke off, do you remember talking about different types of cleavages? What would we have?
Like that one would be
heterolytic cleavage.
Yeah.
Because both of the protons are going to stay with the oxygen.
Yeah.
Okay, so and then of course we would need some kind of resonance structure where see that bottom oxygen would have 3 lone pairs, and then we're going to have to get resonance throughout the entire structure to stabilize the molecule that's left over, or at least the ion that's left over, and that would be our acetate ion. And so, of course, we know with our carbon structures, we have plenty of resonance that can occur. So that's what. So this proton is acidic.
Okay. Okay. Yeah, it'll be comfortable leaving.
Mm-hmm. Here's a fun one.
Okay. Oh.
Abbreviated H4-EDTA. Now, you'll have heard of EDTA.
Yeah.
If you've watched the Blade movies, you've heard of EDTA. This is the compound that made vampires go kaboom.
Oh, cool. It's like, yeah, it's something to do with bombs, right? Like,
no?
No?
I think well, it was a movie, so I don't know if it's correct. I'm not a biochemist. In the movie, they said it was an anticoagulant.
Okay.
But whether that's true or not, I don't know.
I have no idea.
That I would need either a biochemist or a medical doctor.
Okay, so all of those carboxylic acids will do
Mhm.
So this one, it has 4, so it's like it can neutralize 4 equivalents.
Yeah. So if acetic acid was monobasic, what is this one?
Tetrabasic.
Yeah. Yep, tetrabasic. So let's kind of, and again, let's take apart the name to see if we can. So you have N prime, N prime. So what does that mean?
They're attached to the nitrogens.
Yeah, so you have the N on one side, N prime on the other side. And why do you have N and N prime, N prime? Why do you have 2 of them?
It has to do with like the way they're like oriented. It's kind of like a chiral thing, right? Like,
No, it's just because each nitrogen has 2 groups bonded to it.
oh, okay. Oh, okay. Okay, I see.
So now, ethylene diamine, where do you see the ethylene?
It's the one connecting the two nitrogens.
Yeah, it's that center. Now, a lot of people expect to see a double bond when you see ethylene. However, we can't have a double bond because the carbons actually have another bond going off to the nitrogens. But that center group of that CH2 bridge, that's a common ethylene group.
Mm.
Okay. And your diamine, that's pretty easy. Those are your nitrogen groups. Tetraacetic acid.
Yeah.
Where are the acetic acid groups?
They're the other things coming off.
Mm-hmm. They're attached to the nitrogens, which of course would be with the CH2s would be actual full-on methyl groups if you didn't have the attachment to the nitrogen. Mm-hmm. So just kind of a deeper look at how we name things. And you can start to see in chemistry, we name things like German, where it's like, let's see if we can get a name that has 15 syllables in it.
Yeah, I like it.
Okay. Okay, so these acids are going to dissociate in the same stepwise pattern as like our common acids like sulfuric acid. Now we're going to be talking about Kas, Kbs, pKas, and pKbs. So a lot of the times once you get into higher level, people will talk in terms of pKa and pKb, because again, the smaller, the lower, I guess. So maybe smaller is not the best word, but I'd say lower, because you'll see what I mean by that. Mm-hmm. The lower the pKa or pKb, the stronger the acid or base respectively, because we can go negative with those. But it's like a pKa of -11 is stronger than a pKa of -3. But you might say that the -3 is smaller than -11. So I would say lower is probably a better term than smaller. So we have to think about, so ethane dioic acid. Okay, so here's a fun one. So there's a new suffix for you, dioic.
Dioic.
Uh-huh.
Is it just because like there's two of them? Like
yeah, there's two what in particular?
The carboxylic acid.
Yeah, this is a dicarboxylic acid.
Dicarboxylic acid. Okay.
So that's what the dioic is going to mean. What would you say basicity? Well, not basicity, but let's see. This one was tetrabasic. This one was monobasic. What do you think about this one?
Dibasic.
Dibasic. Okay, so and then let's start to kind of get an idea of how stuff like this breaks down. First, let's bring back our methane, our acetic acid, to kind of get an idea of what these are going to break down as, so we can get an understanding of the chemical equations. We're going to bring that back. So we'll start with another way to write this is methane, methyl, CO2 with your acidic proton. Get water. Of course, I'm just going straight for double arrows because this is a weak acid. Now we know that we're going to get hydronium. Now, how would I write the acetate ion in this format?
MECO2 minus?
Yep. Not difficult, but I just want to make sure you understand how these notation works. Okay, so then let's look in particular at the ethane dioic acid. Okay, so you said it's dibasic. So how many dissociations will have?
Two.
Yep. So we have to account for both of those. So I'll use the notation they put in the book where they did. So you can just kind of can get an idea that you have the dicarboxyl groups, carboxyl groups. Let's see. Then you have water. Okay. Now we're going to get our hydronium, and then of course one of these will be minus. The other still has its proton. And so then what we can say for this one, the Ka is. So this one is just on the other side of like the really weak of the line between like really weak and starting to get a little bit stronger. So we wouldn't necessarily say this is a weak acid like acetic acid, but it's definitely not as strong as like your H2SO4.
Sure, it's like a medium.
Yeah. And then of course our second dissociation. Okay. So if you're judging these just based off Ka values, I mean, easy question, but which one's stronger?
The first one.
The first one. The second one, if we were comparing this to other Ka values that we know, would you say that this one will actually occur, or is this one too weak to occur?
I think it's probably not going to happen a lot. Like I would say,
it will happen, but not a ton, because so we can make comparisons of things we know. You see that order of 10 to the negative fifth?
Yeah.
Acetic acid is on the order of 10 to the negative fifth. So we can say, well, we know acetic acid is going to go a little bit. So this second one will add hydronium or protons to the solution at about very close to the same concentration as acetic acid.
Okay.
So we can start to kind of judge, well, it will, not ton. Because I mean, acetic acid, most people eat it every day. It's vinegar. Now here's fun.
So you're saying I could drink this?
It wouldn't taste good, but yeah, you could.
All right, cool.
It'd be like drinking, kind of like a strong vinegar. But
that's okay.
Now here's the fun thing about naming. This is called ethane dioic acid. Let's see. What if I wrote what's another name for that?
What's another name for that?
Mm-hmm. More common name. It's an acid made out of I don't know. One of our ions with multiple atoms in it.
One of our ions with multiple acids in it. Oh my gosh.
C2O4. What is the charge on C2O4 if it doesn't have the hydrogens?
2 minus.
Mm-hmm.
Can't remember the name of it.
That is the oxalate ion.
Oxalate ion.
So what would you call this acid then?
Dioxylic acid?
Nope, just oxalic acid.
Just oxalic acid.
Yep. So a more common name that you learn in Gen Chem is oxalic acid, but then of course it's also called ethane dioic. The dioic for the 2 carboxyl groups, and then of course the ethane for the C1, C2.
Okay. Yeah. That's a very like OChem way of naming.
It is. Very, very much so. Okay, now we're going to start bridging into inorganic acids. So purely inorganic. Now, here's some IUPAC naming conventions. We talked oxo acids are made from oxo anions. You have families of oxo anions that you can make acids out of. So see here, you see the chloric acid, the chlorate family.
Oh yeah.
And how that can be turned into all of these different acids that follow the same naming scheme as the family. Then of course you see the sulfurous and sulfuric acid comes from sulfite and sulfate. So don't know, maybe look at these and kind of refresh your brain on how these families work. Because like, I mean, look at the chlorate family. What do they all have in common?
The ClO, and then they'll have different numbers of oxygen. I guess they have all a -1.
Yeah, so that's the main thing they have in common is their charge. So every member of a family has the same charge. Look at the sulfide and sulfate.
Yep.
And then of course, as you're going up the scale of a family, you just add one oxygen each time. Now, like your hypo level is not always going to be one oxygen. Just like here you see your chlorite, your ITE level has two oxygens there, but on sulfide it's three oxygens. So you can't tell by the number of oxygens what the name is. You have to kind of learn the families.
Yeah. I remember this from Gen Chem.
Yep. I'm gonna throw it back in because I saw it in the book. Now, the fun thing is not all hydrogens in an oxo acid are necessarily ionizable. So let's see. Okay, so number of things to go through here. Okay, so the first thing I want to start with talking about like nitric acid, and we'll probably get through this and then have to pick it up on Monday.
Okay.
But so let's say we have. I just kind of want to remember how some of this math works. You know, technically I could use a double arrow if I wanted to, but I will just know that bottom arrow is itty. Why do you think that is?
It'll mostly go forward in the reaction.
And why is that?
Because I guess when the nitrogen has a negative charge, it's pretty okay with it.
So the nitric acid is a strong acid.
Okay, the strong acid.
So one thing you can look up is the pKa of nitric acid is negative 1.64.
What was the medium range for pKa's? Like for Ka's, it was like to the negative third.
pKa's, I'm not sure what the.
I mean, it's a logarithm, right?
Yeah. So if you did if you took I don't know, what was the value? If you take your the negative log of 5.9 times 10 to the negative 2, that would give you an idea of a pKa at a medium range.
Oh, okay. Okay.
So of course your pKa's is the negative log of your Ka. And so if I want my Ka value, I have to do that. 10 to the raised to the negative pKa value. And then of course, what is Ka?
What is Ka? The acid constant,
Yeah, it's an acid constant. Do you remember what kind of constant it is? That's why I went ahead and drew the double arrows.
Like equilibrium constant?
Yeah. And so then of course I want to make sure you remember how we write these.
Oh, for sure, for sure. It's all coming back.
Because you can start to figure out a lot. Because we could take this pKa, get the Ka, we can start solving for concentrations. Now, what is the structure of that equation?
The structure of it?
Just kind of throw out some things that you see there.
I mean, it's products over reactants.
There you go, products over reactants.
But you cancel out any liquids or solids,
right?
So gases, liquids and gases.
So liquids and solids. Liquids and solids their concentrations are going to yield to 1. So we do not include them in equilibrium constants.
Okay, cool.
Okay. Now we're out of time. We'll pick this up again next time and just keep kind of going through acids at a deeper level than we did in Gen Chem. And start getting to more advanced stuff like the acids, because what we're building up to at the end of this chapter is the acids of coordination complexes.
And same with you being my Gen Chem professor as well, is that I can't like pretend I didn't